Good morning to everyone, and that was Buddy Holly, and that'll be the day. And we have a weekend coming up. We're finishing out a sunny but cold Friday, and I have some questions on the homework already. And the numbers that were requested, page 267, 268, 21 was the first one, then 23, and then 73. So what we'll do is look at those first. And for number 21, I need to get the camera set up to do that. Get it focused, and let's see if we can get, okay, Caesar, let's try that. Our expression, 4x to the fourth, 3x to the third, and 2x. And we're going to divide that by 3x squared. Okay, so that's our problem. Let's see if I can get that in some way so it'll stay here on the camera and stay flat enough that we can leave it there. Okay, that's not too bad. Let me write that on the board. So we have number 21, page 267, and the problem, 4x to the fourth plus 3x to the third, a plus 2x technically to the first, and we'll divide that by, is it 3x squared? Yeah. Okay, let's now cut to the board. That's how I see that particular problem. Now, if you try doing long division, putting the 3x squared outside, you're going to run into trouble in the last term. So I'm going to rewrite this as 4x to the fourth over 3x squared. Then I have the 3x to the third over 3x squared. I have the 2x to the first over 3x squared, and then I'm going to simplify each of those terms. So I have 4x squared over 3. The 3's cancel here, and the x squared cancels, leaving me just x. In this case, I'm going to have plus 2 over 3. Now the question, I can either leave the x with the 3 or write it as x to the minus 1. Is there a particular form the text used there? The 3 and the, but with the x down here with the 3? Okay, you could have done it either way. Any question there in here about the problem? Yes?
How would you know whether you should do long division or that? Because I like long division better, but with that problem that works. Is it just something you'll learn visually by seeing the problem, or?
Basically what directed me here was that the power, the degree of the divisor was larger than the degree of the smallest degreed term in the dividend. If I had gone ahead and done this, it still would have worked, but notice in contrast, and we can try this, because it certainly works, it's just I anticipated more problems doing this than, okay, now technically I would prefer to have a 0x squared. In this case, nothing's lost in the process because this is a monomial. But that bothered me momentarily. You saw me hesitate. Now, 3 into 4. Well, best you can do is 4/3. But that's not a comfortable, that's not the way most of you probably think of division. You think, okay, 3 goes into 4 once. No, it goes 4/3. And x squared goes into x to the fourth, x squared. Now that probably is not the way your thought process would work if you just jumped into the problem. Now the next one's a lot better because that's just x. But then you get into this last one, and if you saw the game here, then you understand this is going to be 2/3. But then the question is, what can I multiply times x squared to give me x? And the answer is x to the minus 1. But that is not a comfortable way of thinking, I suspect. So it does not lend itself as well as what we did here in getting the 2 over 3 times x to the minus 1, or just having 2 over 3x. It can be done. Now to answer your question, what would you recommend? And we might just come out a little bit in that, Caesar. Yeah, good. Which would I recommend? In this problem, what I did here, because I think it's a lot less confusing. How do I know to go to that? Again, the argument was I looked at the lowest degreed term in what's called the dividend, I looked at the degree of this divisor. The degree is more than what I had here. So to avoid some of the complications, this might be the better way of seeing it. And then the other question, if you start this and say, what in the devil am I going to do with 3 into 4? Then maybe say, okay, is there an alternative that I can do that would avoid the confusion? Fortunately, you tend not to do much of this. Before I answer the question, let me just go one step further. If you were to see this numerator, very seldom are you really going to be placed in a position short term where you would divide by something like this. For the most part, you're going to be looking for a common factor in this, and you're going to say, gee, there's x in every term, so I'll pull the x out using a distributive property and rewrite it in factored form. There are times as you go on in mathematics where we do look at ratios of two different expressions, two different polynomials. And we may indeed do precisely what we did here. In those problems, this would be the preferred form. Rarely would you go to this. Now, I say rarely. I can think just off the top of my head at the moment of one particular problem in calculus where you would be inclined to do long division in this form, but it's not very often. So, rule of thumb, look at the degree of each. If this is a larger degree, go here and see what happens. Now, Pam.
Well, I was just going to comment, could you just say if you're dividing by a monomial to just into a polynomial just to
It's probably the simplest way. Yeah, as a rule of thumb, if you're dividing by a monomial, write it as a combination of fractions. And for a short term, it deals with it at an appropriate level. Long term, you may have to change slightly. And one of my concerns, and it's a guiding kind of influence in everything I say and respond to, whatever I tell you, I don't want you to have to change 5 courses later. So to that extent, I'm a little bit bothered by saying, okay, we're just going to do it this way and not provide the alternative. So a little bit uneasy about that. But nevertheless, let's go on to 23. Let me get that under the camera first, Caesar, and then we can look at the problem. And I don't know if this is going to merit, well, this camera and the angles I'm getting are not cooperating at all. Let's see what I can do. And bring that down tighter. Okay, there's my expression. It's right at the top of the page. And you don't see the problem number. That's 23. But now, as I see this problem, first taking general rule of thumb, dividing by a monomial, so what are you going to do right out of the gate?
fractions.
Write it as fractions, where you're just going to take the sum of what's going to be 1, 2, 3, 4, 5 fractions. Now, going on the other basis, coming back to Lorna's question, if I look at the 2, its degree is 0, and the degree of the denominator is 1. So again, the same thing, so I'm not sure it merits going much further in that problem. Treat it exactly as we did in 21. Thank you, Caesar. Is there any further discussion of that problem? Okay, 73 is the next one. And again, trying to get things so I can see what we need. Okay. Now this one should be much more straightforward as we look at this. This is 73. I have a trinomial divided by a binomial, and this is exactly the problem we illustrated in rather extensive way yesterday. Let me write the 2a plus 6 out front. And then inside this division symbol I've written, I want 3a squared minus 11a plus 17. Okay, we can cut to the board now. And it's just a matter of the long division algorithm. That is, you look at the 2a into 3a squared. My guess as to why this problem was requested is exactly the problem we had that you can see above. And that is, you're taking a 3 into a 4 and wondering, how in the devil am I going to do that? How am I going to take a 2 into a 3 here? The answer is you get 3 halves, a. And you have to think fractions. That is not the way we think of long division. I mean, I don't know of any time when you talk about arithmetic that you think of it that way. So that's a wrinkle that is going to be unsettling, and hence the reason for the question, I suspect. In particular, you hope that this 6 in some way is going to simplify with that 3/2 when I multiply and not get a fraction. So let's see what we get. We take the 3/2 a times 2a. That's going to give us 3a squared. Fortunately, the 2 in a denominator will reduce with the 6 giving you a 3, so you get plus 9a. Now, if your comfort level with fractions is, as often the case, that just may feel totally uncomfortable and cause the sense of, what do I do? Change the signs, and we are going to go ahead and add. Now, I add the 3a squared to negative 3a squared and get 0. So I have a 0 here. And then in this case, I have what? Negative 20a. And this problem sort of takes care of itself once you get past that first term in the quotient, which is your answer. Because now 2a into negative 20a, and I should, my apologies, bring down the 17. And there's another wrinkle coming up here that's important to us. But if I take the 2a into negative 20a, I'm going to have a negative 10. So I'm going to put the negative 10 up here. That's negative 20a. And you may feel betrayed at this point, because you have, in so many cases, had things work out nicely at the end. And say, okay, we get zeros across the board, and lo and behold, 77. And it's like, okay, what do I do with the 77? Well, you say, that's my remainder. So you say plus, and then you say 77 over 2a plus 6. Just like when you divide 3 into 100 and get 33 and 1 left over, you say 33 and 1/3. Now that process right there does become important. Because what will happen eventually, you're going to ask a question we asked in here at an earlier time. What happens as this value of a would get larger and larger and larger? So you're going to let a get very big. What's going to happen to this fraction? If a gets very large, the fraction is going to get smaller and smaller as a gets larger and larger. Eventually, this is going to become so negligible that for a large enough value of a, say a is 1,000,000. So 77 over 2,000,006. We would just say that's 0 for all practical purposes. And we would argue that you just get this expression here, to the left of where I'm pointing. That becomes a line. And so we say as the variable gets larger and larger, you're getting a line. And that is a very important concept later on in mathematics. So this particular problem illustrates very nicely the kind of answer that we often get. That rather than being the anomaly, rather than being that rare case when things didn't work perfectly, that is a reality more common than what you would expect, a remainder of 0. Any further discussion in here? Okay. An illustration of what I'm talking about there. Okay, I'm sitting here with the straight edge lost. So we'll just sketch a vertical line, horizontal line. You recognize that as a what? Coordinate system. Okay, XY coordinate system. And we have talked about how we can graph the equation of a line, meaning how I can go ahead and find the solution for a linear equation in 2 variables, plot the ordered pairs, and they're on a line. There are other models. That, by the way, is called a linear model. So, for example, you might argue that if you want to find what y is, you double it. That's a linear model. So if you're going to double your price to get the selling price, otherwise take your cost and double it. It's a nice way of doing business. I pay $1, sell it for $2. Okay, and if you can do that consistently, you'll probably get rich. So I buy something for $1, sell it for $2. My equation, the price as a relationship to the cost is y equals 2x. We call that a linear relationship. We've talked about it as direct variation. If I look at a problem we've talked about, and I've talked about it as powers of 2. We did it the other day, where you have Sessa's reward. You get 2, 4, 8, 16, 32. We talked about that same problem looking at Pascal's triangle and finding the sum of the entries in a given row. Being very careful how I say this. That gives an equation. It's 2 to some exponent, 2 to the first, 2 to the second, 2 to the third. So with all that said, I could argue that my equation is 2 to the x. Now that is not linear. We refer to that as exponential. It's called exponential because the variable is an exponent. It's that simple. Now this is the powers of 2. We've seen it in Sessa's reward. We've seen it in the sums of the entries of Pascal's triangle. If a population, such as a city in California, doubles every 10 years, we call that exponential growth. So if Modesto is at 20,000 and 10 years later is at 40,000, and 10 years later is at 80,000, and 10 years later is at 160,000, we talk about that as doubling every 10 years. That's exponential. World populations have a tendency to grow that way, and that's where we are looking at what's potentially going to occur 20 years from now or 50 years from now, and they're projecting 10 billion people. At one point, they were projecting 12 billion. It's dropped down to 10 billion because fertility rates are dropping right now. If I look at the curve, and I just want you to be aware of this curve. Think of a jet plane taking off. Out of Modesto going to Stockton. Okay, you immediately go up. The runway's short, so you take off, and you look like you're nearly going vertical. That's exponential growth. Now the question is, what happens to this as x gets bigger and bigger and bigger? Well, at some point, populations have a tendency to hopefully level off, and that's what's arguing now. But if I argued that this became like a straight line, instead of just getting exponential, gradually became linear. So it sort of, at some point, then does this. That's an advantage, because you can't see that on the screen as well as I'd like. If it becomes something like this as time goes on, we're saying it becomes linear instead of exponential. That is what I'm talking about in this expression, where this 77 over 2a plus 6 goes to 0, and you get a line. That's the kind of thing I'm talking about. Now, what we are arguing may happen is this, and that's called logistic. And that's where your population levels off. And this happens very much in product development, because if you produce something, your growth, if it's a product that's in great demand, will continue doubling. And then at some point, market does what? Saturates, and then you level off, and that great growth you had levels off, and you no longer are making money hand over fist. Now, in the software industry, what do we do at that point? Bring out a new release. So again, you can do what? Take off again. And Microsoft has done very well with that. And you try to make sure that the product is incompatible to the previous edition. And if you do, everybody has to buy it. Okay? And you just keep playing this game and hoping that everybody goes along with it. And this is what's happened with the operating systems in the computer world, where we've gone from DOS to Windows 3.11 to Windows 95 to 98 to 2000 to XP. And Bill Gates is sort of continuing to count on that everybody will go into the next release. And of course, what's the counterpoint to this in the software industry? Linux. Free. I read yesterday about Bbox, which is a release that is very robust and was done for a company who wanted something in a counterpoint to Windows, and then the company in the IPO stage and everything that happened went down, but the Bbox as a OS, an operating system, is still floating around as sort of an alternative to Linux. So, interesting. This whole concept gets tied together with what we do in marketing and in sales, and again, looking at that idea. How does the algebra tie together with the real world? The world population and its growth exponentially is a major concern, and of course, making money is a very big concern, and you hope that your growth is exponential. You double your sales every month. That's great until everybody has the product, and then suddenly, no more sales. Well, that takes care of the questions I was asked from the voicemail and email. Are there other questions in here regarding that set of problems? Perry?
I had 73, but I was looking at 63 and 51.
Okay, 63 and 51. 63 and 51. Okay, 63 is that wrinkle where you've got to be very careful that you do what first?
Include your zeros.
Placeholder.
Okay, first,
Oh,
before we even get to that, I'm going to try to, let's see if I can darken that. Is that too much? That seems to look better. You have to go down the same way. If your denominator has r squared as the first term, you want to rewrite the numerator so it's r to the fourth. Minus 2r squared plus 5.
them in descending.
So you'll want to have both of them in descending order. Now, as a rule of thumb, I would also have in the divisor r squared plus 0r minus 1.
But it works without it in this one.
Yeah, in this one you can manage it. You can get by without it, but in general I would.
Get in the habit.
Okay, now, coming off there for a moment, Caesar. You could put 0r into it, and in that numerator, or the dividend, you could have had a term for r cubed, 0r cubed, and 0r, and it turns out you don't need them in this. But at this point in your introduction to algebra, to having the insight when you're going to need it, when you're not going to need it, is maybe not as clear. So as a kind of general approach, maybe put those missing powers into the problem, and if you don't need them, it doesn't hurt you. But if you leave them out and you need them, you're going to get confused. So as we go back to the problem, what tells me that I don't need them, okay, this is dicey, but let me write the problem first and then respond to it. We have 5 minus 2r squared. Every time I have to erase like this with my hand, I pay for it when I go ahead and try to create your photos, because then it looks like heck on the screen. Here goes. This is number 63. Now, I'm just going to share with you as we come back to the board now what I'm doing as I look at the problem and make a judgment, do I need to change it? If this doesn't set well with you, don't get upset, okay? This is an attempt to answer a question, and it may not fit everybody equally. I'm going to let the infamous LET, I'm going to let, what letter do I want here? W equal r squared. I could have used V, U, S, T, any letter I want. I'm just using W. I have no justification. It's the first letter that came into my head. But now look at what I have. 5 minus 2w plus w squared over w minus 1. Am I missing any powers? No. That's what I was seeing when I saw the problem. I did a little substitution in my head and said, well, if r squared was w, I'd have 5 minus 2w plus w squared over w minus 1. I'm not missing anything, so I'm okay. As I said, this may not fit everybody. But is that answer enough for the question, or do you want me to carry it further, Perry?
Just a little further.
A little further. Okay, let me write the r squared minus 1. I'm going to leave it in the form it was given, but I am going to write r to the fourth minus 2r to the second plus 5.
I think the problem I had was that I left out the r or the 0r in the...
That's okay. It'll work because of what happened here, but let's carry it.
Okay.
Shouldn't be a problem. R squared goes into r to the fourth. R squared. Agreed? Okay, so if we get the r squared there, the r squared times r squared is r to the fourth. It's sort of a who's buried in Grant's tomb thing. Then minus what? R squared, which goes right under the r squared above. Change the signs, and again, this may seem like an unnecessary step to you, and you may feel, I want to cross out that minus sign and make it a plus. Don't do it. When you go back and look at a problem and follow your steps, you want to note that you made the sign change, and if you just put a vertical line through the minus sign, you don't know if you changed the sign or not.
And the reason behind changing the sign?
You're subtracting. To subtract one polynomial from another, you change the sign of everything and add.
Negative 2r squared.
Minus becomes a plus, so I have negative 2r squared plus r squared, which is negative r squared.
Because originally it was a negative r squared at the bottom, correct?
Right.
Okay, I see.
And if I subtracted, I'd have parentheses around that, and each sign would change. Is that okay now?
Yep.
And then from there, are we okay? Yes.
That's where my confusion is that changing of the sign right there messes me up when I'm doing the problem when I was doing last night's
Okay, let's see if I can write it in a different form for you and see if we can give a little better visual.
It makes sense when
Well,
you're
but
doing
now
it
let's see if we can do
forward.
visually what's happening. Isn't this what you are saying in that step? You're taking what was here and subtracting what you obtained when you multiplied r squared times r squared minus 1. So I had r to the fourth minus r squared. I'm supposed to subtract that from what I had above. So that means I have a minus sign outside the parentheses. So now it's that negative sign in front of a parentheses, and there's two ways of thinking of it. Switch the signs inside, or think of it as a minus 1 times everything inside and use the distributive property. But I then get r to the fourth minus 2r to the second minus r to the fourth plus r squared. And that's exactly what I had here. The r to the fourth becomes a negative r to the fourth. I had the minus 2r squared, and I have a plus r squared. It's just I have them now not underneath each other. But I would get negative r squared out of this. So if you're having trouble with that on the side, maybe write this out for a while. And then you'll get very frustrated doing that every time. And then you'll say, well, okay, I'm going to switch the signs in here because that's a lot faster. And you've solved the problem. But if you're getting caught here, then revert to this step so you aren't getting trapped. And eventually it'll groove in. The practice making a permanent, perfect solution. Any other questions on the problem? Okay, there was another one, 61, right? Is that correct?
No.
51.
51. Okay, well, let's take a look just to see if there's something that we can key on that'll give us some insights as to... Oh, mercy, how am I going to... Books sometimes don't flatten out very well.
I think the question I had was, I
Amen.
the remainder and that you've explained.
Okay, well, let's see what we get here just for a moment. I'm trying to flatten this out. Okay, let's see what we have here. Now, everything's in the right order. This is 51. The 2a's going into the 4a squared, and then at the end, I assume you had something left over because it doesn't look like it's going to go nicely.
Right.
And then, what was your remainder out of curiosity? 74. So you would write plus 74 over 2a plus 3.
I think
Yes.
the question is, how did you get 74? I had 64, and I don't know where the 74
Okay,
is
you
from.
got 64. Is there an agreement that it should be 74 or 64? Okay, so the question is, how do we do that and get that? Where am I going to go? Okay, Caesar, we're going to have to travel. So if you can, thank you, come to the document cam and let me travel. 51. So we've got a question on the remainder. And by the way, that's sort of a nice thing to have to be stuck on if you're going to have to be stuck on something. The process you're feeling good about, I hope. And the question is, do you feel stuck at the right point? And this is one of those things which I'm sort of, okay, it's a nice place to be stuck. As you look at this, is there anything that would give you any insight that you're going to have a remainder? Let me explain again what I see. Not that I expect you to see it right now, but what I'm seeing is trinomial, second degree. This is a binomial first degree. I know I'm going to have a binomial when I get done at least. The last, otherwise I'm saying 2a plus 3 times something. Now I know it's going to have to be a 2a to get what? 4a squared. Now the question, this is a negative up here, this is a positive here, and that's a positive. I'm in trouble. If I make this negative here, I'm going to get a negative at the end instead of a positive. If I make this positive here, I'll never get a negative here. That's the first observation I made. Second observation, 3 times something has to be what? 32. No way. Nice way of stating it. There's nothing in terms of just an integer that you can multiply by 3, it's going to give you 32. So I look at that problem immediately and say, okay, this is not going to go well at the end. Now those are the kinds of things that, as I say, you aren't going to see right now, but eventually they become the kind of intuition that says, okay, it's reasonable to have a remainder. So as I do this division and take 2a plus 3 into the 4a to the second minus 22a plus 32, I do not have great hopes for a nice clean solution. I have a 2a here, so I have a 4a squared plus a 6a. Now I hope that at this point you're doing those kinds of steps pretty much without even furrowing your brow, not even getting upset. You change the signs or you rewrite the step if you prefer. Now, what do I get here? I have a negative 22, a negative 6, so that's a negative 28a. Now that makes me feel a little bit comfortable because 2a will go into 28a, and so that's sort of nice. I'm going to have a negative 14, correct? But I can see immediately I'm in trouble because 14 times 3 is 42, not 32. And furthermore, I'm getting a negative instead of a positive, so I've got all sorts of trouble. Okay, so negative 28a and a negative 42.
So my question's moved now because it was a math multiplication error.
Ah, okay. This is going to become a positive here. This is going to become a positive, and indeed I have the 74. Now what do I do with that 74? I bring the 74 up here as a plus 74 over the divisor, which is my 2a plus 3, and that is all I can hope to do. Yes?
Carol, each time you move into a different quantity, you have to change the signs like this.
Each time I subtract, I change the sign and add. And remember, if that's an uncomfortable step, then on the side, rewrite what you had on the top minus what you were subtracting. So what I'm saying again, you have over here on the side 4a to the second minus 22a minus 4a to the second plus 6a. That's what's going on in this step. This minus outside changes each of these inside. That's why I changed my signs to negatives. Okay? Any other comment there? I think we're ready to fold and pass, so I'll let that stay up there. Now, because of trying to get ye photos up on the website for the weekend so you can reference all the board work. I spent my time this morning trying to get that done, and I don't have your papers to return from yesterday. So it was sort of a trade-off. I'll try to have everything back for you on Monday. And if we can just sort of bring them up maybe towards Perry, and then Perry can pass them to Pam, and then we'll eventually get up close enough. At some point, I can do something about it. The next one. It's nice to have something light at the end of the week. Well, okay, now whether or not you agree with the next statement, let's go to the document, Cam. Scientific notation. Now, I am hoping this is not the first time in your life you've seen scientific notation, because we go into this extensively into Math 10. We come back and look at it in Math 20, and it's getting to the point in our society where if you're using a calculator, you can't avoid the notation. And I've tried to illustrate that in a problem where we talked about combinatorials, and you look in the calculator and you see a 10 to the 36th. In particular, the problem that we talked about, how many ways could you take 200, and I think it was 200 countries, 30 at a time, came out at 8.9 times 10 to the 36th. So the question, what is our rule that we follow for doing a number in scientific notation? And as we come to the book at the bottom of 270, I don't know if this is familiar to you in terms of the process. I'm going to leave that for a moment. I'm going to go to the sideboard, and we're just going to look at something. First, the number I wrote the other day. 8.9 times 10 to the 36th. By the way, remember on the calculator, the way it was written, and I had rounded off, it had 889. There were a few more digits, and then it said E36. What that was telling you, not that you had error number 36. This was not an error code. It was saying multiply by 10 to the 36th. Now, all this tells you is that you're going to move this decimal point to the right 36 places. Question, why do we have scientific notation? Now, there are a couple arguments for it. One, there are some numbers in science that are what we call constants, that are just too darn awkward to use in any form but this. For example, we have a number that is something times 10 to the 23rd. So let's just say for the moment I had 5, and this is not the correct number. But that's the way the constant is learned. I'm thinking of Avogadro's number in chemistry, and for the moment I can't think of the digits here, but my recollection is it was 10 to the 23rd. And it has to do with moles and chemistry and so on. You wouldn't want to write out 23 zeros after 5 every time you reference the number, so it's just a shortcut. The other, and of course, in history of mathematics and science, large numbers were commonplace enough that this was a nice thing to do. It was not very often that we had to work with terribly small numbers. For example, when somebody says you have 1 millimeter, you understand that's 1,000th of a meter, and so you may or may not feel awkward doing 1 over 1,000. And for the most part, if we do feel a bit awkward about that, we just say 10 to the minus 3. And we introduce the negative exponent. We've talked about that. But there are times as we look at a world that is, in a sense, going the opposite direction of large. We're talking about microtechnology and the development of computers, and if you look at some of the things they are producing now, it's just amazing. The number of circuits they can put on something smaller than your fingernail on your little finger, and literally put thousands of such little circuit boards in that space. We are starting to talk about very, very small numbers, and we talk about how fast something happens. We used to think, well, a blink of an eye was fast. I mean, if you blink your eye, you missed it. Now you can miss it 15 times in a blink of an eye and still overestimate badly the amount that should be there. So it is not uncommon to see numbers that involve a great many zeros before you see what we call a significant digit. And so we make some agreement as to how we are going to write such numbers, and the agreement we make is that the decimal point comes after the first non-zero digit as we go from left to right. So we know we're going to write it in the form 8.9. And we know we're going to multiply times 10. The argument is you want to be able eventually to get this decimal back to where it was. If you multiply by 10 to a positive exponent, the decimal goes to the right, as we talked about up here. But I want to go to the left. I want to go how many places back? Well, I want to go 1 to get to the left side of the 8, and then how many more? 1, 2, 3, 4, 5, 6, 7. I'm going to have to go 8 places to the left to get back home. Home being where it was. Now that is as simple as I can state it. The decimal comes after the first non-zero digit. You must multiply by 10 to some exponent. The exponent is determined by which direction you go to get home. Home is where the original decimal was. The decimal was here, and to get home I go to the left, so it's a negative, and I went 8 places. If instead, and let me just take a number up here that is large, but certainly not as large as what I had in this problem, you don't see a decimal point. And you may say, well, that was a nice rule, but there's no decimal point. What you are not remembering is there's always a decimal where? At the end of a number if you don't see it. So it's there. You just may not recognize it. Now, I want the decimal after the 8. It's the first non-zero digit. Now, how many places must I go to get back to where it was? It's 6. Hence, I move 6 places to the right, and now I have it in scientific notation. That's the agreement we make. There are other ways of writing the number, but they wouldn't be in what we classify as scientific notation. Now, there was a time when working with scientific notation was essential, particularly if you were taking courses in chemistry and physics. Now, this was about, I'd say realistically, 25 years ago. That's BC, before calculator. Okay? If you go back to 1975, 76, a calculator was not a given. A TI data calculator, $100. Today, you get them free in the mail. But then it was $100, and all it did was add, subtract, multiply, and divide. It would do a problem in percents and have one memory. That was it. Maybe do a square root. I think it did a square root. I think it was called data math. It used batteries. It was the size of, well, not the size of a 10 key, but we think of a graphing calculator you buy now. It was that size. It wasn't the little piece you can put in your pocket or put in a briefcase and lose it because it's so small. And it used batteries. And it was $100 when $100 was more of a price than what you pay now. Yeah, well, let's think. A car in that time, a pickup was $3,000. $30,000. So multiply by 10. So that's not bad. That'd be about $1,000 in today's money to buy a calculator to do addition and subtraction, multiplication and division. So you didn't buy them readily. And in a few years later, you could buy, well, about the same time, within a year or two, HP came out with their series. And my recollection is that that was $300 at the time, $300 to $400. And that calculator now you can buy for $20, and it does more than it did then. So that's one of the nice things about technology. But what was used before the calculator when you were in science? Okay, that's not a bad answer. But the real prestige thing to carry around was a slide rule. I mean, you hung it from your belt like a badge of courage. And if you're an engineering student, 10 years before, now we're talking before 75, go back just 10 years, and you paid $30 to $60 for a slide rule to do the calculations. And before that, scratch paper. So yes, but the slide rule had been around for quite a while. Now, let's look at the kind of problems you might do in science at that point. You might have a problem where you take this same 8, 9, 0, 0, 0, 0, 0 times, and let's say that just for the sake of argument, you were going to multiply that by this number, and then divide by, I'll do this a little bit easier. And you want to know what the answer is. The slide rule would give you 3 digits. It wouldn't tell you where the decimal was. It just give you 3 digits. And by the way, the old 10 keys didn't set the decimal for you either. They just gave you, at many times, just the digits you needed. So your question was, how big was the number? Well, the way you handled a problem like this was to rewrite it in scientific notation. So you said 8.9 times 10 to the 6th times 2.5 times 10 to the what? Okay, the decimal I want after the 2, so I'm going to have to come back 4 places, so -4 over 7.5 times 10 to the 3rd. Do you understand how I converted to the scientific notation? Now what was nice is the 2.5 went into the 7.5 3 times. I rigged it. 3 goes into there about 3, so I know the answer is going to be about 2.9 times something. Now, the question is, times what? Well, I have 10 to the 6 plus -4 minus 3. I'm dividing by 10 to the 3rd, so subtract the exponent. I multiplied by 10 to the -4, so I added the exponent. So that's 6 minus 7, so my answer is 2.9 times 10 to the -1, so my answer is about 0.29. All the calculator would show you is a 2.9. You had no idea where in the world to put the decimal point. So survival depended on your ability to use scientific notation. Some people would argue those days are gone by. Well, all I can tell you, there are complicated problems you work in chemistry and physics where you can't enter all the garbage into your calculator because the numbers are too large. And you often have to enter them in scientific form in order to do problems in the physics, chemistry, and biological areas. So it's not something that is just of historical interest. It has validity. And if you're reading the newspapers, and I know that you're probably busy enough that that doesn't happen, but if you had time on your hands and you weren't doing an algebra class and everything else that's going on in your life, and you were to read newspapers and magazines and keep up with things like what happened in the Columbia tragedy, and you look at the write-ups, oftentimes you see speeds that are being talked about. So many times the speed of sound, and that was the big issue. And you're talking about being a certain amount of feet in the air and such. Some of those problems lend themselves to scientific notation. And of course, one of the big issues right now in budget, not California, but in terms of what's being proposed, what kind of deficit are we talking about currently when Bush and administration is talking about the deficit that may be facing us with everything that's going on, because they're talking about tax cuts when we're going to spend a lot more. So it's a little bit weird in a way. We're going to have to spend a lot, so we'll cut our revenue. What kind of numbers are they kicking around? Multiples of trillions, $10+ trillion. Well, how are you going to write 10 trillion? Well, obviously, if you want to write 10 trillion, you can say 10 trillion.
That would be
That's the easy way. But you say 10 trillion and you don't have an idea in the world about how large that is. So it's big. It's more than you have in the bank. Okay? So we have 10. Then we say 10,000, 10 million, 10 billion, 10 trillion.
There we go.
There we go. So that as a power of 10 we could do. So let's say they're talking about 70 trillion, and I heard some numbers up in that range. So let's say it went instead 70 trillion. Then the question, how would you write it in scientific notation? And maybe this gives you a better idea of the deficit. Okay, this sort of goes beyond most of our abilities to think of just how big this is. 1, 2, 3, 4. 4 times 3 is 12, plus 1, 13th power. And I don't know if that's impressive to you, but at least it is big. And you have a little better idea of how big it is than if you did what? 70 trillion. So if I'm writing something in the newspaper, I've got to make a decision. Do I want to write it as 7 times 10 to the 13th? Or do I want to write it as 70 trillion? Now I can take it out of the same context, and let's say that your number is really this. Now that is 72 thousands, millions, billions, trillions. So it's 72 trillion, 130 billion, 465 million. But that's roughly 7.2 times 10 to the 13th, and this is going to be better understood than all this garbage. Now, by the way, those are realistic numbers of what we're talking about of the deficit. And that's the future. That's for next year. Okay, now after trillions comes quadrillions. By the way, I usually do this in a math 10, and just let me throw this in as a minor point. M in the Roman system was 1,000. And if you wanted 1,000 thousands, you put a bar over it. So 1,000 thousands was 1 bar over the M. If you wanted 1,000 thousands, 2 bars. Now 1,000 thousands. Give me another name for 1,000 thousands. Oh boy. Yeah, that didn't work well at all. Here's my 1,000 thousands. 1,000 million billion. 2 bars. 2 wheels is called a bicycle. Hence billion. If I have 1,000 thousands, I'd have bar. So I have bar M. That is like tricycle, so that is a trillion, which we call a trillion. And that's what goes in the naming of these. So, yeah, I heard that okay. Anything you say. Now, basically, what is written here in your presentation is a restatement of what I've done. And then the effort is to have you do some problems of a similar nature. And so what we have in mind as we look at some of these, you're supposed to mix and match on page 272. This is not a toughie. 4.6 times 10 to the minus 4, and you're supposed to look at column 2 and find the right one that goes with it. Let's try the first one at least. What goes with 1? A, B, C, D. Which is your choice? A. I have 3 people agreeing. This makes me feel less secure than I planned. That is a correct answer. Okay, but at least the idea is just ask yourself how many places would you move the decimal point if you have a negative 4. And the idea is you'd take this negative 4, move this 4 places to the left. So that means the first one takes you on the left side of the 4, and then you have what? The 3 zeros, and that's indeed what you get. So let's come off there. Then the typical thing after we've asked you to recognize something, then try to rewrite something in what we call positional form without scientific form. So what are you going to do in that first one? 4.56 times 10 to the third, you're going to move the decimal 3 places to the right, so you're going to have to do what? Add a 0 and say it's 4560, and the decimal point will be changed to a comma. Coming off that, then you get to go in reverse form. So on 15, you have a mess, 5,876 with some zeros, thousands, millions, billions. That's 5,876,000,000. You want it in scientific notation, so where does the decimal go? After the 5. So 5.876, and then you have to move the decimal how many places? 9 to the right, so you have 5.876 times 10 to the 9th. Coming off there. Then we work backwards again in the next group. Okay, off there. And we come down to the next group, and then you do the kind of thing historically that I was illustrating on the board. They're not quite as bad as what I had on the board, but to give you some practice, so if you hit a course in science, this would not be something particularly unsettling. Now that's as far as we're going to go. We're going to take 1 through 44 odd. That's a fairly short assignment, so you should enjoy the weekend and understand that we also finished Chapter 4. So then the question is, where do we go next week? Okay, the key word I've been leading up to for some time. On page 288, factoring, the reverse of the products we've been doing. So that's where we're headed. So on that happy note, Caesar, we've been listening to Buddy Holly, and what's the choice? Think it over. I agree. Have a great weekend.